So this is lecture 9 in engineering mechanics. We are going to continue with our problems in equilibrium of concurrent forces in a plane. So the problem that we have been discussing is problem page 23, problem number 8. It is about 3 rollers, equilibrium of 3 rollers. Okay. I'll drop this out. Page 23, problem number 8. So the problem is about 2 smooth cylinders, each of weight W is 100 Newton and radius 6 centimeter, are connected at their centers by a string AB of length L is equal to 16 centimeter and rest upon horizontal plane, supporting above them a third cylinder of weight Q of 200 Newton and the radius of that is also 6 centimeter. Find the force S in the string AB and the pressures produced on the floor at the points of contact D. So the figure is given like this. 3 cylinders are there. 2 of them are on the floor. Then 1 is above, resting on it. The weight of the 2 cylinders, or the one which is on the floor, is 100 Newton. So this is marked as point A. This is B. There is a string which is attached. The weight of this is 100. This is also 100. This is 200 Newton. And you have the rollers or the cylinders are considered to be smooth. Then we have now the radius of each one is given as 6 centimeter and the string length is given as 16 centimeter. Now you have to find out what is the tension in the string. So I have shown you this thing using a 3 tins like this. Now if you see, when you put 2 of them here, they may be in equilibrium because only the weight is acting. Now you put the third one above this, third one, so that is not in equilibrium, right? So there is nothing to support the horizontal forces, so that made this to fall like this. Now if this one has to be in equilibrium, what I do is I connect the bottom, this thing, using a string. So in this case it is a rubber band. I have put the rubber band here. So I put the cylinder above. They are in equilibrium. Okay. So it is necessary to have a string to keep this in equilibrium. I hope that this won't fall till the exercise is over. Now this is the case So we have to find out what is the tension in the string. So for solving this, we can just think of, trying to have the free body diagram of all the three cylinders together. Let us see any immediate help is there, because if you try to do three cylinders, then we have to do it three times, three free body diagrams, etc. Instead, if you try with a single one, maybe you get a simplified or short cut method. So I draw the free body diagram of the three cylinders, then mark what are the forces which are acting. This is the weight, that's 100, 100, here you have 200 Newton, and of course there will be a tension in the string which will be like this. This is a tension in the string. So you have here the reactions from the floor. So that point we can consider as a point which D and E. So you will have RD and RE here. So you can say this center as C. Right. Now with this you can think of the first ask a question whether it is whether a system of concurrent forces. Okay. So if you think of this as a system, whether it is a system of concurrent forces, it is not, because here these are vertical forces, they will never meet and reach a point of concurrency. So you cannot say that if the force polygon is closed, then that is the necessary and sufficient condition for the system to be in equilibrium. And next question is number of unknowns. There is a tension here. These two, this tension is equal and opposite. So if you use a law of superposition and say this can be removed, this force need not be considered for your analysis, you can remove it, then you are left with this thing only. Okay. Now if you look at it, the number of unknowns are only 2. So you can definitely solve this. If you draw the force polygon for this, all the vertical forces in the down, so you have 200 plus 100 plus 100, that is totally 400, and by given the symmetry of the system, if these two forces are has to be same in magnitude, so we can straight away say that this is going to be 200 each. Okay. But the question of finding the tension in the string cannot be solved. Okay. It is not just solving for the two reactions from the floor, but you have to find out the tension also. But you cannot say still that this is going to be in equilibrium. Okay. So we have to consider now the free body diagram of each cylinders. As I told you, this is a free body diagram. When you take the section at the middle where you consider the forces, the center of gravities are lying. Now let me take the free body diagram of the lower one and upper one. So free body diagrams. The cylinder with the center A. So you have here 100 Newton, then you have here RD, then you have here the tension which is represented as S, then you have another force which is applied by the upper one here. So I'll call this as, if I name this as first cylinder, this is second, that is third, I can call this as reaction from 3. So this is a free body diagram of the cylinder, the one which is there in the lower. The second cylinder, if you think of, you can see the vertical forces, only this will be in the different direction, but apart from this is going to be same. So if you do the analysis for this cylinder, this will also hold good for this cylinder because of this symmetry. Now I will take the free body diagram of the third one. Free body diagram of the third cylinder, which is the center is represented as this. You have 200 is the weight, 200 Newton. Then you have the reactions coming. This is going to be R1, this is R2. So here look at this here, the number of unknowns are, don't know the number of the unknown, magnitude of RD, you don't know the magnitude of S, you don't know the magnitude of 3, so 3 unknowns. Here you have, if you know the directions of R1 and R2 from the geometry, only 2 unknowns, so this is solvable. So we can first solve this free body diagram, this solution, you can get R1, R2, then we can proceed for this thing. So if you want to solve this, you need to know what is the angle at which the force R1 and R2 are applied. By symmetry, you know, R1 and R2 are going to be at the same angle. So if I say this angle as alpha, can I determine that alpha from the geometry of the problem? So I can construct a triangle connecting the 3 centers of the cylinder. Now I have a triangle which is A, B and C. So this length is given as 16. Okay, so I have to put so this side is going to be the sum of the radius of the 2 cylinders. In this case they are equal radii, so 6 plus 6, so it is 2 times R, so you have 12. So this angle is going to be alpha. So you can say that from here this is going to be 8, that is half of this. Okay, so you can write that cos alpha is equal to 8 by 12. So you can find out what is the angle alpha from that, is it not? So the alpha is going to be 48.18 degrees. So you can calculate and check the angle, 48.18 degrees. So now I think for space requirement I'll rub with this. So you have this alpha. Now I can construct the force polygon for this. I have the 200 Newton, the weight of the top cylinder, which is like this. Then you have R1 like this. You can have this at this angle. So this is to be closed. So this is the tail, and you have the head here, tail and head here. So this is going to be R1. This is going to be R2. So this angle, what it makes with the horizontal is 48.18. So I can find out the other angles, that is 41.81, and this angle is going to be 96.38. So using the sine rule, I can say R1 by the sine 41.81, that is equal to R2 by sine 41.81, that is equal to Q, or this 200 by, you have this sine of 96.38. So from this you know that R1 is equal to R2. So R1 is also equal to R2, that is equal to the 134.16. So that is the value of the reaction between the top cylinder and the bottom cylinder. Okay, so we have found out R1, R2 as 134.16. so we know the magnitude, we know the alpha also, so this process is completed. So this is a system of concurrent forces. This force polygon is closed, means this will be in equilibrium, no issue. Now coming to this cylinder at the bottom. So cylinder at the bottom, you have R3 is just now, R3 is going to be equal to and opposite to R1. So this magnitude is going to be 134.16, and the angle that it makes with the horizontal is going to be alpha, that is 48.18. So you see here this problem is reduced to the number of unknowns are the magnitude of S and the magnitude of RD. So only these two are the unknowns. Now I can construct a diagram for say 100 Newton, that is the weight of this. Then I can draw this S, I can draw this RD, I don't know these things, okay. Then I know this here. So I can maybe starting here at this point, I can draw this at an angle of 48.18 with the horizontal. This is going to be magnitude of 134.16. Then from here a vertical line, then you draw the horizontal line and vertical line. This is going to be S. So this can be constructed geometrically. So if this is to be closed, you have the arrow gate here and arrow gate here. So RD has to be like this and S is to be like this, that is pulling this cylinder in this direction. Okay, so you have any doubt, you can stop. So I'll rub this up. Now you have this the thing, only you can say that yes. So you have here, this is going to be, this side of this is going to be equal to S. So 134 S is going to be in by magnitude is equal to 134.16 cos times cos 48.18. Then RD is going to be equal to Q plus sine the 134.16 into sine 48.18. So Q is this is 100, okay, 100 plus this. So this RD is 100 plus this amount, that is going to be sine part of it. So this is S is going to be, by calculation you can say 89.45. Then RD is going to be 199.98. So we have completed whatever is required, the reactions from the floor, that is going to be 199.98. So that is, it's supposed to be 200, but because of the inaccuracies in calculation you have got this. Okay, this is 89.45 is the tension. So we have completed whatever is asked. You have any doubt? Okay, now we have other two problems. Suppose we can take it up and solve. The problem is at page 19 and problem 1. Page 19, problem number 1. It is an example problem where it is already solved. So it is about like this. You have a street light. Okay. So you say this is point A, this is B, this is C, this point is D. Okay. Now this is an electric street lamp The problem statement is an electric street lamp is suspended from a small ring B supported by two wires AB and CB. AB and CB. The ends A and C which are on the same level. So these two are in the same level. Then assuming these wires to be perfectly flexible and neglecting their weights, find the force produced in each if the weight of the lamp is 15 Newton. Weight of the lamp is 15 Newton. The length of each wire is 10 Newton. 10 units. So here it is given in feet, so I can take just as 10 unit. Then the sag dB is 4 unit. So I can take this as 10 meter and 4 meter, right? No issue. So this is the problem. You have to find out the tensions in the two ropes. Okay? So it is a suspension like this. Now if you look at this point B, that is a small ring and two wires. So this particular point, if you look at the force interaction or free body diagram of that ring, you have a force, that is the weight, which is acting as 15 Newton. Then you have two forces which are acting like this. So here the idea is like you can find out what is the angle this makes with respect to the horizontal. So if you say the tension in this are say S1 and S2, then you can find out this angle, right? This angle alpha can be found out. And since you think of this triangle, which is an isosceles triangle, which is here it is 10, here it is 10, this is going to be 4. Okay, so this is A, D, C and B. If you want to find out what this makes with respect to the horizontal alpha, so you can readily say that tan alpha is equal to, sin alpha is 4 by 10. So you can find out what is alpha from this. Okay, so it is going to be 23.57. Alpha is 23.57. So here we know the alpha, that alpha is going to be the same here because you also have a 10 and a 4 here. So it is the isosceles triangle. So you will have this also is going to be alpha. So by this diagram, by drawing the force polygon, so this is going to be 15 Newton and you have something here at alpha. You can draw with respect to this thing is also going to be alpha. So they will be intersecting at a point. So we can find out this is to be close. The arrow should be like this. So this will be your S1. This will be your, okay, if you say this is S1, so this is going to be S1, this is S2. So they will be equal. So you can find out this, this is alpha is going to be 23.57. This angle is going to be 66.43. Okay. Now we can say that 15, this angle is going to be 66. Okay. So 15 by sine, this is 47.15. So 15 by sine 47.15, that is equal to the S1 by sine 66.42. That is also equal to S2 by sine 66.42. So if you see this from this, the R is 18 or S1 that is also equal to S2, that if you work out it will be 18.75 Newton. So we can find out what are the tensions in the rope like this. Okay, so the basis is we ask a question whether it is concurrent and a planar forces, and you have the three forces like this, then you can construct the force polygon and that should be closed. Finding the angle from the geometry given, you can find out like this. Okay, so you have any questions? Now if somebody wants, I will redraw this force polygon. You have this force that is 15 Newton is the weight of the lamp, and you have the two tensions. That is S2 and S1 with the angle, what it makes is alpha. So the alpha is related to this sag. Okay, somebody wants to have less sag. He don't want to have the sag of 4 meters. He wants to have the properly stretched one, so that there is a sag. He wants to reduce it. So if he wants to reduce the sag, what will happen? What will be the alpha effect on this alpha? Alpha will be less. Okay, if we want to reduce the sag in this kind of arrangements, the alpha value will reduce. So in that case, this will result in lower alpha. So the alpha, if it is lower, let us see what happens. So your S2 and S1 will increase. For the same weight of the lamp, if you try to reduce the sag, then S1 and S2 will increase. So if you want to reduce the sag further, then you can think of, this is going to be very large. If I reduce this alpha further, so this is the effect you can see. So if you take the strings for suspending something, if you keep on pulling this two ends to have a less sag, means it will break. If the tensions in the two strings exceed, so whatever be the weight can be less, but if the angle is less reduced, it may tend to break the wires. Okay, so we will discuss about it, because when you are lifting the materials using cranes, the slings used have a certain angle. Okay, otherwise the slings will break and the parts will fall on the people. That is very dangerous. Okay, so the effect of this sag is very important. Okay, now there is another point. You have any doubt about this? So you can see the effect when the polygon is to be closed. You can see that the S1, the value is increasing. As I told you, that force is a non-conserved quantity, that even for 15 Newton you may have some 60 or 100 Newtons tension in the rope. Now the other part. Okay. See, if these two strings are there, okay, in this problem we have taken that A and C are at the same level, so that it will occupy the middle. The length of the two segments of this ropes are equal. Suppose it is not. If I keep them at two different levels, okay, so A is here, D is somewhere else. A is here, C is somewhere else. Here I know that if I try to hang this thing, the equilibrium point will not be at the middle. Okay, it will be somewhere else. So if that is the case, how to go about it? How to solve this? Okay, so that is the next problem given. But okay, so I have a string here. I'm hanging some weight here like this. Okay, so I'll put it on this at an equal height, so I should not be. So I'll put it like this. So what is the equilibrium point? If they are same level approximately, it will be at the center. Suppose I do it like this, what happens? So it finds a new equilibrium position which is not at the middle point. So like this. See, I keep this constant and I say I raise this, it reaches a new equilibrium position, right? Okay, so I'll do that. So that is the previous problem is something unique of this, where they are at the same level, so it has occupied the middle. Okay, here we are ignoring the friction between the two. Okay, friction is ignored, then you see that it occupies the different positions. So here the next problem is about that. That is the problem at page 21. Page 21, problem number 4. So this is also an exercise problem where example problem, this has been worked out already. So what is that problem? Let me read it. A chord A, B, C. So in this case it is, this point is taken as B, this point is taken as C. The chord of A, C, B, the length of 20 meters. So the length of ACB is 20 meters long, is attached at points A and B to the vertical walls, which are 16 feet apart. So this is the vertical wall. The distance between the two walls is given as 16 meter. A pulley of C. So here you can think of a pulley so that it can move around. It is not, earlier case it was a hoop where it is attached, but here you can move around. As I told you, instead of a pulley I use just a hook which can also slide around. So this is attached. A pulley C so small that we can neglect its radius carries a suspended load of P is 36 Newton, and it is free to roll without friction along the chord. Determine the position of equilibrium as defined by the distance x. This is x. And the tensile force in the chord. And the one of the other information which is given in the figure is this distance is, so this points are marked as G and H. This point is H. So this is about 3 meters. So that's it. So how to solve this problem? So you have to find out the distance x. As I shown you that it will take not in the middle, somewhere else. So you have to find out the distance x. So when you are looking at the problem and trying to solve the problem, you cannot move further unless you make some understanding about the nature of the forces that are acting. Now ignoring the pulley radius, we can say that the force weight and the tensions in these things are concurrent. If you say the pulley radius is large, it will be difficult. So you can say these are all converging at a point. Then you can say the tensions S1 and S2 are the two tensions in this. So what will be the nature of the tension? That is the first point that we have to understand. Then what will be the angle alpha 1 that S1 makes with that, and alpha 2. So that understanding is the beginning that is required to solve the problem. So here, if you look at this equilibrium of this particular point, that is the bottom of the pulley or the pulley itself, you consider that it's having a negligible dimension, then you have this P that is equal to 36 Newton. You have the two tensions, right, S1 and S2. The angle it makes is alpha 1 and alpha 2. So what will be alpha 1 and what will be alpha 2? To find out alpha 1 and alpha 2, I have this x, but I should know either this distance, okay, to find out this, or this part of this chord to find out it, but that is not known, okay. So here the important thing to be discussed or to be understood is the nature of S1 and S2. So here, if you think of the S1 and S2 should produce equivalent force for the P, okay. The effect of S1 and S2, the tensions in the string should produce an equilibrium force, so that the net of these two should produce a vertical force that cancels this P, okay. So in other words, if you resolve this S1 and S2 into two rectangular components, namely the here if I resolve this into two rectangular components, okay, so see, you will have a horizontal component, this will have an horizontal component and a vertical component. If you resolve this into two rectangular components, and you will see that the two vertical components, the sum of the two vertical components will be equal to this P equal to 36. Okay, so that is the equilibrium force. The sum of these two will be producing equilibrium force to cancelling this. But what about the two horizontal components? If this system is to be in equilibrium, the horizontal components by themselves should be in equilibrium. Otherwise, the system cannot be in equilibrium. Okay, so from here we can appreciate that the horizontal components of the S1 and S2 must be in equilibrium. Therefore, their magnitude must be same and they must be equal and opposite. Okay, must be equal, that is same, and it should be opposite and collinear. So that is not a problem. They are acting at a point, they can be horizontal, they are collinear. That magnitude must be same. So you have to say that this magnitude must be same from this. So what will be the nature of S1 and S2? What should be the S1 and S2? That is possible if you have this alphas are same and S1 and S2 are also same. Okay, it can have a different alpha here, then you will have these two are this to be same. Here that is not possible. So only possibility here is that the tensions in the two ropes S1 and S2 must be same and the alpha 1 must be equal to alpha 2. Okay, so alpha 1 is equal to alpha 2 and the tension also equal to be same. Then only their horizontal components will balance each other. See, apart from this, I think this another argument that we can put for S1 and S2 should be same is that it is a continuous rope. Okay, the continuous, this is not attached anywhere, there's only pulley rolling on it. The continuous rope should have the same tensions. Okay, so taking this alpha 1 alpha 2 are the same, then we can say this is also as alpha 1, this is also S1. Then we can proceed in a better way. Now what we can do is, now we extend this from here, extend this point and say this point is D. We can construct a triangle from this. So you can say this, you do it here, this intersection point you can say is F. So if you take this this is going to be your angle alpha. Now you can take this as alpha, this is alpha, this is going to be symmetric, this is going to be alpha, this is alpha, this also will be alpha. Okay, so this length dB is your original length ACB. Okay, this are an isosceles triangle, so this and this will be same. So you will have that AC and DC are same, therefore this length DCB is equal to ACB, that is equal to 20. So that is an important thing. So here if you look at that triangle which is BDF, here that is alpha, this is 16, this length is 20. So from this we can determine what is alpha, and this point is your G and H. So this is known, this is alpha is known. So this distance GH can be found out. Okay, so if you look at that, the tan alpha is equal to, from here you can construct the cos alpha. So from this, cos alpha is equal to 16 by 20. So alpha is equal to 36.86. So that is your alpha. By looking at this triangle, we can say that tan alpha is equal to 3 by GH. Therefore GH is equal to 3 by tan 36.86, that is equal to 4.00. So GH is 4. So here again, if you look at this triangle, this is X, this is going to be X, then your 16 is equal to 2X. So this will be making, this is alpha, this is alpha, so this also will be making an isosceles triangle. So this distance is X and this distance is X. So you will have 2X plus GH is equal to 16. So we have found out GH is right now as 4. Therefore we can say X is equal to 6. So we can do like this by the calculation. Now if you take the other aspect, that is the force polygon, to find out the tension, we can say this is your vertical weight, that is 36 Newton. Then we have the two forces, this angle is alpha, that is 36.86. So this angle is going to be, so you will have a tensions like this. So this angle is going to be 73.72. So this angle is going to be 53.14. So you can say this S by is a tension S divided by sine 53.14 is equal to 36 divided by sine of 73.72. So from this S is equal to 30 Newton. So this is an example problem. You can have a look at it, then can come out. So we have taken up and solved a few problems in concurrent forces in a plane. So next class we will go for the method of projection, that is tomorrow.